All right, let's look at another example. This example is a little bit more realistic than the stone wall that we saw, previously, right? This example is about groundwater levels data in a region. Now, groundwater levels data in a region, when we think about groundwater, the issue with groundwater is very similar to the coal, seam beneath the surface. Well, what is common is that, both groundwater and coal are blind to the naked eye, right? So when we look down, we know there is groundwater, but we can't really know what is the structure in which it exists, and what's the flow, direction, what are the different, dimensions of groundwater, in the way it exists beneath the ground. So here is a schematic, a picture that has been sourced from the US Geological Survey, and it's a very old picture. This picture sort of goes back to 1896. But this picture is very informative. If you look at what's happening here is that we have the ground surface, right? So ground surface by itself is quite irregular, right? And beneath the ground surface, of course, you have this rock structure, right? I mean rock or sand structure, right? The dotted area. And beneath the dotted area, the rock structure, we have what is called as the aquifer, right? Aquifer by itself is extremely irregular, right? Now the aquifer, the way it exists is that it stores water at times as tubs which are large in size, or as tubs which are small in size at different elevations, right? So if I were to start, drawing water from this source D, and I start drawing water here, very soon this water will deplete, and I'll start seeing the rock or the aquifer surface. And if I were to solely, base my, estimation of groundwater levels on location D, then perhaps what I'm going to say is that this region does not have a lot of groundwater, and most of it has been depleted already. But if I were to go to locations E and F, I will have a very different conception of what's happening with groundwater levels in this region. So what this figure is showing us is that the aquifers exist as these tubs that contain water in different volumes and shapes, right? When it will rain, let's say when the precipitation happens, what's going to happen is maybe at the elevation the water will start to slide down, and probably from here it'll start entering the aquifer region and sort of replenish the groundwater, right? At times, aquifers are also such that water exists, between hard rocks, right? I mean, so this tub here is, a domain by itself. So if you were to draw water from here, you would have to really dig down deep, until here to be able to draw water from here. But this location A is very, very different from this location B. Well, probably A1 and B1. I should be careful about notation here, right? Perhaps they are not stationary because the source of their replenishment for B1, which is going to come from here when through precipitation, for A1 it might be coming from somewhere else, right? So we should be very, very careful before we go on to assign stationary domains for groundwater levels, right? So having sort of seen a picture, a very, very complex, perhaps a very complex picture of the way or the structure in which groundwater exists, let's move forward and try and assess the quest for stationarity for this surface. So the exercise that we are doing here is that we are asking, can we delineate the factors that impact spatial stationarity of groundwater data? And we are saying specifically for Uttar Pradesh, India. Okay, so I'm talking about this region in the pink boundary, which is the state of UP in central India, and I'm trying to see if I can delineates the factors that impact spatial stationarity of groundwater data. We have seen these data previously when we were doing, we did an extensive exercise of exploratory data analysis with these data, right? So, so we have seen the data, we have seen some of the characteristics of these data, what are the different levels and so on and so forth. We know that the green dots are, representing, not so deep water depths. Whereas, and the color goes from yellow to orange to red, we are looking at, worsening groundwater level situations, right? Now the question is, where are the stationary domains in these data? Is the entire state a stationary domain in itself, right? Should I be sort of, dividing the state, in let's say four equal parts and call each of these domains stationary? Should I divide them, vertically, or should I be dividing them horizontally, right? What should I do? Quite clearly, such a decision should not be arbitrary, right? Because once I define my stationary domain, only then can I say the average, level of groundwater in that domain. Unless I have claimed or argued out that UP is spatially stationary, I cannot say what is the average level of groundwater. So the mean statistic is not defined unless I'm able to, claim stationarity. Okay. Now, okay. So clearly, we need something more than arbitrary, demarcation of stationary areas. And as we have seen earlier, perhaps we need expert domain knowledge. And one of the expert domain knowledges is the knowledge of aquifer types. So one of the things about the aquifer in UP is that it is an alluvial aquifer. Right? What is an alluvial aquifer? Well, what it means is that there is very high lateral movement of water between these tubs. So these rocks are porous in nature. That is, water is all the time traveling across these rocks, right? If they were non-porous, if they were non-conductive, then the water capacity of what can be stored in these rocks will probably just depend on what's falling down from the surface and what's being extracted for irrigation or domestic purposes or industrial use, right? But if they are porous, then the water levels are connected everywhere, right? So the UP region in general is the alluvial aquifer and hence quite porous. That is not to say that, that then we can just, blindly, that's a question, can we now blindly assume that UP by itself is a spatially stationary domain as far as the groundwater data are concerned, right? Well, what we will see is probably not, because there are other factors to worry about. Okay. So here is another sort of a data on aquifer, thickness in meters across UP. So what we are seeing here is, so the NCR region is, so this is New Delhi here. So what we see is that the region which is nearer to New Delhi, the aquifer is not so deep, right? Not so thick. So that capacity of storing water is not so high. But as we move, eastward, there are very, very deep aquifers to be found. Of course, there are some patches of not so deep aquifers in the east location as well. But largely, moving eastward, I have much more density of deeper aquifers than I have on the area that is proximate to New Delhi. So there is a lot of media news of groundwater depletion around Delhi in the NCR region. Well, a lot of it could be urbanization demand, but also could be that there is less water retention capacity or water storage capacity of aquifers near the Delhi region. All right, so based on our discussions earlier, now let's try to identify factors that impact spatial stationarity of groundwater data, right? So now we discussed, we looked at an aquifer structure. So aquifer structures can indeed be very irregular in space, right? What we have seen till now is that you could have the aquifer containers could could have different types. For example, they could be alluvial in nature. They could also be clay-y in nature. So if it's clay, it doesn't allow too much lateral movement of water, right? The other thing we saw was what is the thickness of the aquifer. That is to say, what's the water retention capacity of an aquifer, right? So these are spatial characteristics of what's going on beneath the surface when we try to understand the groundwater dynamics or how groundwater levels evolve beneath the surface, right? So one factor that we are sure of that we will have to have an access to expert knowledge is on groundwater hydrology, right? Specifically, what we have seen here is aquifer type, right? So we saw that this could be alluvial in nature, this could be clay in nature, they could be hard rock, right? There is no movement whatsoever, and so on and so forth. Second, we saw a map on the thickness of aquifer, which is nothing but the water storage capacity of an aquifer. There are more factors that groundwater hydrology will guide you to regarding aquifer properties. It's also important how fast the water moves from ground surface. Let's say if there is precipitation, how much and how fast will it actually enter the aquifer source of water, right? So clearly hydrology is important for making a decision on whether or not a region or a sub-region, a stationary domain for groundwater spatial analysis, right? What can be the other factors? Well, one of the things that came up in our discussions just 5 minutes ago was that there could be different structures of demand for groundwater or consumption of groundwater, right? Near the for the UP state, near the New Delhi region, right? So the areas like Gautam Budh Nagar, areas like Meerut, and so on and so forth. What you expect is a lot of groundwater demand is going to come from domestic use or industrial use, right? So that demand is going to be very different from, let's say, if I go into the heartlands, towards central Uttar Pradesh or eastern Uttar Pradesh, where majority of the demand is probably going to come from, agricultural irrigation of groundwater, using groundwater, right? Now these uses, that is domestic, industrial, are characteristically different from agricultural. Agricultural use is mostly for irrigation. It is also seasonal. It depends on crop cycles. When do you plant a crop, who does plant a crop and who doesn't, right? So there's a lot of human decision making going on in terms of consumption of groundwater in different regions. So the second very, very important factors that will drive whether or not a domain is stationary for groundwater discharge is going to be the human dimension or the human impacts, right? These can also be termed as the anthropogenic factors of groundwater dynamics, right? Well, you can have the exactly same hydrology beneath the ground, but if you put a farmer on the top or a leather factory or a sugar factory on the top, you can expect very different groundwater levels dynamics at those two locations, and we should not treat them as the same domain. So we should not probably assign them the same average or variance statistics or whatever, right? So we should probably have a different statistics, summary statistics for urban regions with a given aquifer type, and a separate one for agricultural regions with a maybe as the same aquifer type, right. So these are now we are looking at pairs of factors that we should be looking at when we are assigning stationary domains within the Uttar Pradesh region. The third factor is obviously the rainfall, right. More generally, we can say weather, right. For at a given time period, if it's a good rainfall year, well, you can expect high recharge. If it's a bad rainfall year, it's a drier patch as far as the weather is concerned, then you can expect the water levels to be slightly lower, because the demand is sort of is ongoing whether or not it rains so much. In fact, if it doesn't rain so much, for agriculture, groundwater provides a substitute for for cropping needs, right. So you may have even more vigorous discharge in lower rainfall years. So lower rainfall years will have sort of double whammy for agricultural regions as far as the groundwater levels are concerned, right. So certainly different seasons so far as the rainfall levels are concerned, monsoon, non-monsoon, pre-monsoon, post-monsoon, perhaps they should be considered different stationary domains, in order to sort of delineate, summary statistics like mean, variance, standard deviation, the fifth percentile, the 25th percentile, the 75th percentile, and so on and so forth. Okay. So what we learn through this exercise of looking at groundwater levels data is that spatial stationarity assessment depends on context, right. The first thing we learned was that spatial stationarity assessment depends on scale, okay. And the second very important learning is that the spatial stationarity assessment depends on context. If I were to look at coal seam data, oil exploration data, groundwater data, population data, education data, crime rates data spatially, all of these different contexts will involve domain knowledge in order to make the decision of stationarity, right. And it will matter, what will also matter is what scale are we making that decision at, right. What is or what is not a stationary domain depends critically on these factors, okay. So it's a complex decision, we cannot avoid it, we cannot run away from it. In fact, it's the first decision that we must make before we move on to assigning summary statistics or conducting data analysis or so on and so forth. Okay. Okay. So now I want to move on to the second sort of part of this lecture, which is where I will give you formal definitions of stationarity, mathematical exposition of stationarity. The first exposition that I want to talk about is called as the intrinsic stationarity, right. So I start with the spatial data model, something that we have seen before. What we are looking at is a random variable z at location S, right. So we have at every location S there is different levels of z that we can expect to realize, and each realization, potential realization of z at location S will happen with a given probability, right. And S is in a given domain, and domain is a d-dimensional space. So we will always sort of simplify our life, and let us say we work with a two-dimensional domain. Okay. So here I have data at different locations, right, and and the data are at each location are given by a random variable z S, and small z at this location S can be thought of as a realization of this random variable, right. And we are S is simply the index also, so every location is unique, so I can just call it location 1, location 2, location 3, location 4, all the way to location n, right. Okay. Then intrinsic stationarity is defined in terms of the first differences, okay. Intrinsic stationarity by definition is defined on the first differences. What is the first difference? Well, z at location S and z at location s plus h, right. What is h? H is the spatial lag. Okay. H by itself is a vector. That means it encompasses both distance and direction, right. If I have if I am moving from s to s plus h, I have the distance as well as the direction. I can have a value of z s plus h prime where the distance as well as the direction will be different, right. The property on which intrinsic stationarity is based is the first difference. First difference meaning zs minus zs plus h prime, zs minus zs plus h. Now, intrinsic stationarity holds when expectation zs plus h minus expectation zs is equal to 0. What does it mean? It means that expectation zs plus h is exactly equal to expectation zs. That means the mean value at each location is exactly the same. Remember, we are pooling data in space to be able to comment upon summary statistics, centrality measures at each location. So, the first assumption for intrinsic stationarity is that the mean value for z of s will be exactly the same no matter which location I am looking at, right. So, whatever the shape of distribution, the mean, wherever the mean lies, it will be exactly the same for all locations, right. This is obviously the first moment property, right. This is the first moment property for intrinsic stationarity. The second moment property is the variance, obviously, and the variance of the first difference, that is zs plus h minus zs. Now, on average, that is in expectation, that is what we have said, in expectation the values zs plus h and zs will be the same, right. Of course, for a given realization they can be different values, but in expectation, if you were able to sort of sample at the same location 1000 times, keeping everything else held constant, right, at the same location, same world, if you are sampling again and again, on average each location will yield you the same value of groundwater level or the coal quality or the coal quantity, whatever you are working with, right, whatever the context of your problem, right. Now, but the difference, the variance and difference could be different, right, it is the second moment. Now, the second moment property says the variance of zs plus h minus zs is equal to what we call as 2 gamma h. So, where the expectation of first difference was independent of either the value zs or the lag vector h, the variance of this difference does not matter on the location, but only the distance between the two locations S1 and S2, right. So, the second moment of the first difference between these values in space, any two pairs will solely depend on the lag between them with inside this function gamma h, right. Now, this 2 gamma h is perhaps the most important parameter of spatial statistics. Okay. It is called as the variogram. Okay. So, the variogram is of course coming from variance, it is a device by itself, it is an operator by itself, right. So, the variogram basically is the variance of the first difference of locations of pairs of locations across space for a given domain of spatial data, right. Now, this variogram only depends on h, it does not depend on z, right. It does not also depend on the location, it depends on the distance norm between two given vectors S1 and S2, right. You can sort of call s plus h as s S2 and S1, and you can sort of think of any two locations in this domain. So, this is true for every S1 and S2 pair in domain D, which is subset of the two dimensional real space. Okay. All right. So, we have learned the variogram, we have looked at the property of intrinsic stationarity. Okay. Let us move forward. So, I am going to just repeat this one more time. First of all, intrinsic stationarity is defined in terms of first differences. Second of all, it depends on the first moment and the second moment operators, expectation and variance. Okay. Variance of Zs plus H minus Zs yields is equal to 2 gamma H, depends only on H, only on the lag vector, depends only on spatial lag. If it depended on locations, that is to say that it also depended on, let us say, S, that is which location are you starting at, then it would not be intrinsic stationary. Okay. So, it can only depend on H. Okay. Now, stationarity or intrinsic stationarity again is a decision, it is not a hypothesis. I am saying it again and again, so that we do not fall in the trap of actually trying and testing intrinsic stationarity. Okay. So, intrinsic stationarity is not the only type of stationarity, there are other forms of stationarity in data. The second one that we are looking at is called as the second order stationarity. What does second order stationarity mean? Well, let us just draw our domain D again and think about data samples from the locations represented by these crosses in domain D, right. Let us say we are looking at location S and location S plus H, right. I can also call this S1 and I can also call this S2, right. H by itself is a vector, it is the difference between S1 and S2. Remember, what I am writing is a L2 norm, and we have seen at the earlier half of this course that this norm, that is the distance between locations S1 and S2, can be measured as Euclidean distance, as Manhattan distance, as great arc distance, and so on and so forth. Okay. So, H again captures both distance and direction. Okay. Now, the first condition for second order stationarity is that expectation Z of S is equal to a constant for all S in domain D. This is very similar to the first order condition, first moment property of intrinsic stationarity. This is exactly the same, by the way. That would mean, this would imply that expectation Z S plus H minus Zs, which will be nothing but expectation Zs plus H minus expectation Zs. Why can I take the expectation operator in? Because it is a linear operator, right. So, it can simply enter in. Now, both S and S plus H lie in domain D, hence expectation values will be constant at both locations, and what I get is just a 0. This is exactly the first moment property of intrinsic stationarity. The second moment property of second order stationarity is different from intrinsic stationarity. It depends on the covariance operator between locations Z S1 and S2. Remember, S1 is S and S2 is S1 or S plus H, okay, S plus H. Okay. Now, what is the difference between the variance of first difference and the covariance? Now, it turns out they are related. Now, if I were to sort of write down, I am going to try and write down the second order property, the second moment property, second moment property of intrinsic stationarity is variance of ZS1 minus ZS2 is equal to 2 gamma S1 minus S2, where previously we had just equated this to this value h, right. Now, this would imply the LHS can be written as variance of Z of S1 plus the variance of Z of S2 minus 2 covariance of Z of S1 minus Z of S2. This is equal to nothing but 2 gamma h, where h is simply the distance between S1 and S2, right. Now, this is interesting. Now, you have you basically see that the variogram, right, the variogram, this is my variogram, and here the term covariance ZS1, oh sorry, it is not minus, it is sorry about this fumble here, 1 second. Okay, Z of S1 comma Z of S2, right. Okay. Now, this term here is my what is called as the covariogram, which you see right here as the second moment property of second order stationarity. Okay. Now, the covariogram and variogram are related, and the way they are related is that now variance of ZS1 is nothing but you can write 2 gamma 0, because you have the distance between these two is 0, right, not sorry, not 2 gamma, 2 twice of sorry about that. Okay, it is covariance with distance 0. This one variance of S2 is also covariance with distance 0. It is just covariance of SZ at S2 with Z at S2, right. So, we have C of 0 sitting at both terms here. So, now you can see that the variogram and the covariogram are linearly related. In fact, they are simply inverse to each other. Okay. What this means is that if the covariance of values at two locations is high, the variogram value will be smaller. That is quite intuitive. Well, if the difference between two values, well, expectation of the values is the same, but if the variation in the difference of values is high, then you would expect those values to be less related, and hence the covariance will be smaller. If the variance of difference of two values at two locations is small, that means there will be much higher spatial dependence, and hence you will have the covariance to be high. So, if the variance of ZS1 minus ZS2 is small, then spatial dependence is higher, and hence the covariance of ZS1 and ZS2 is also higher. Okay. Now, this is interesting, right. I mean, now, so you have this mirror image properties of second order properties defined as intrinsic and second order property of stationarity, second order stationarity. Now, these two definitions only differ by these two factors, and these factors have appear to be linearly related to each other, just linearly negative of each other. But they are specifically different because covariance is a linear association property, right. So, covariances only sort of provide a measure of linear relationship between the value Z at location 1 and location 2. Okay. Variance, on the other hand, is highly nonlinear. So, there is a stricter assumptions required in order to sort of assert the covariogram, the covariant stationarity or the second order stationarity in space. And therefore, intrinsic stationarity is considered to be a stronger property than the second order stationarity property, right. That is why the last sentence on this page says second order stationarity is also known as the weak stationarity or wide sense stationarity in a spatial domain. Okay. All right. Let us move forward. There is a strict stationarity, strict spatial stationarity property as well, or the strong spatial stationarity property as well, and this property relies on the joint distribution itself, right. Remember, we are when we are working with spatial data, we are working with these random functions, right. So, you have data at location S1, you have data at location S2, S2 is nothing but S1 plus H, right, right. And what you are saying here is that you have the distribution of marginal distribution at each location, the marginal distribution at each location, they are connected spatially. So, the data, all of these data in this domain are jointly distributed. If these joint distributions remain exactly the same, even if we were to move the data by a lag, right, from some locations we sample S1 to SM and we evaluate the empirical CDF. Then we move on to a different set of locations, again m data points, but with a lag. Let us say we move 5 steps eastward, right, and we define an empirical CDF. If they are exactly the same, we say the data, that is S1 to SM and S1 plus H to S1 plus SM plus H, which is 2m values, define a stationary, strict stationary or strong stationary domain. Okay. Now, we seldom use such a strict stationarity property. Usually we are working with we are working with intrinsic stationarity. So, we will see that most of our discussions going forward will rely on this variogram device to measure spatial dependence and to be able to model it and then take it to regression analysis for further resolving further issues. So, remember, in summary of this lecture, the validity of any summary statistic in space, that is the mean, variance, variogram, semi-variogram, covariogram or whatever, depends on your decision of stationarity. We cannot avoid this decision, it is the heart of spatial statistics. I started this lecture with this comment that spatial stationarity is the heart of spatial statistics, and I am repeating it now with a lot more knowledge at your at your disposal. Now, decision of stationarity is, however, highly subjective and complicated, right. You need to argue it out in a rigorous manner. Expert domain knowledge and contextual knowledge is unavoidable when dealing with spatial data, right. Just like any other data sets, here we have we have to be cognizant of expert domain knowledge, right, probably more so in spatial data because of the subjectivity involved. All right. So, going forward, we will be now working on measuring spatial dependence or spatial contiguity from the next lecture, and I hope you had fun in this lecture. Thank you for your attention. See you next time.